Okay, Bismillahirrahmanirrahim. So let's start our today lecture. And in the previous lecture, actually, we finished our uh, derivation, which was about the particle in one-dimensional box. So we ended the lecture over here. So I have just put the both equations over here, and this equation is about the particle in one dimensional box, and we are discussing the wave function, and wave function is important over here, and you must know the difference of the particle in one dimensional box, and this is the equation we have achieved up to now. And with the differentiation of this equation and with the second differentiation of this equation, we have moved up to right now. And in a similar equation, we have derived in earlier lecture when we were deriving the Schrodinger wave equation. And this equation was like this: psi will be equal to a sine 2 pi x over lambda, and this is also a psi, and this is a wave function. So you must understand what is the difference between these two waves. This is the in one dimensional box, like this is the box because we have restricted the particle in one dimensional box, and there is only one dimension, mean we are considering here the x-axis. But in this case, when we derive the Schrodinger wave equation, and where we consider the angular velocity or the angular movement of the particle in a circular path with the 360-degree angle, and that's why there was the maximum distance covered in a circular path, that was 2 pi. And this was the equation with the angular velocity, and this is the equation with the one dimensional box. So you must not be confused over what we have done earlier, and now we are sorry, moving to the particle in one dimensional box. Because why we are considering the particle in one dimensional box, because we are going to now further explore what is the translation movement of the particle, or the translation movement of the electrons in the different orbitals. So this is our main objective. So we are considering this as a main equation, and then further modifying the equation and getting the value of the wave function in one dimensional box. So I am further proceeding with the equation. So actually here, what is the value of A and what is the value of K? These are unknown. X, we know this is the position at the x-axis, but we do not know what is the value of A and the K. And our main target in this lecture is to find out the value of K, and then we will move to the value of the K. When you know the value of K and the value of A, of course, you can get the value of the wave function. You can calculate the wave function, and this is very, very important, because you know the value of the wave function if the particle or the electron is moving in one dimensional box along the x-axis. And here K is we will discuss, and if you want to know the value of the K for the Schrodinger wave equation with the angular velocity, actually 2 pi over lambda is the K, and this equation becomes a little bit similar to this equation, but the value of K would be different as the value of K over in one dimensional box, because this is the translation motion and this is the angular velocity. So let's see what is happening with the value of K in one dimensional box. So I have divided this further lecture into two parts. In the first one, we will get the value of the K in today's lecture. And then in the next lecture, we will find out what is the value of A. And then we will further discuss the wave function or the wave function of a particle in one-dimensional box along the x-axis. So this is the equation we have derived, and this is the just I have shown over here. These are the two equations we have earlier derived in the previous lecture, and further I suggest to watch the video again about the particle in one-dimensional box. So what I'm going to do further here, so psi will be actually a sine kx, and yeah, if you have a look over here, this is the second differential of this equation. This is also d square psi over dx square equal to minus k square a sine kx. So I am further I am just putting the value of a sine kx from this equation, because a sine kx will be equal to psi, and this is the a sine kx. So I am just replacing the a sine kx with the psi, and this equation becomes like this. So this will remain the same, and a sine kx will be equal to psi, and that's why I have put over here this is the psi. So this is just the rearrangement of our earlier equation. And now in the previous lecture we have also derived the this one equation from the Schrodinger wave equation, the second differential of the Schrodinger wave equation, that was equal to a minus 8 pi square m e psi over h square. So I have discussed very detailing the equation when we derive the equation. So I again request you or suggest you to clear your concept by watching the previous video, so you would know the importance of this equation when we will be uh, applying this equation to calculate the wave function or the other transitions possible with the transition of the electron from the one state to another state. So this is the new no new equation we have already derived before. So I am just comparing these two equation. This is equation 1 and this is equation 2. Why I am going to compare? Because the left hand side of the both equation are the same. So if this is equal to this is equal to this, that means this part will be equal to this part. Both right part are equal to each other. So this is the just the comparison of the two equation. Now with the cancellation of the wave function and the sign, because here you can cancel out the sign, you can cancel the minus sign. What is left? K square is left, that will be equal to 8 pi square me over h square. And when you take the under root, this will equation will become like this. So and this is the same k we got it from the Schrodinger wave equation. So I am repeating again and again. So there are the variety of the way to calculate the values of k, and then we will actually discuss later on the importance of each of the constant. So now I'm again, actually our target is this, and I'm going to put the value of k and then later on a. So we have right up to now, we know what is the value of k. So I am putting the value of k in this equation and just replacing the k. So this equation will become psi will be equal to a sine 8 pi square me h square under root x. So I'm just putting the value of the k over here. Now, again, you must know what is the mass. Mass is the constant, pi square is the constant, h square is the Planck's constant, E is the energy. So again, this equation looks like more complex because you need the energy of the particle having mass m moving in a translation motion, and you need what is the actually pi is a little bit coming from the when it is the angular movement of the particle. So but here we are considering the x the particle moving in the x direction or the in one dimensional box. So I am further modifying this equation. Actually the value of k I am going to further modify to get it more simpler as compared to what is written over here. So it would be more appropriate to calculate the value of k because here there is no indication what is the dimension of the box or the what is the length of the box, because we are considering the particle in one dimensional box, and here there is no such parameter where you can put the value of what would be the length of the box. So the rest of the derivation I am going to derive by considering this concept. How can I put the value of the length of the box over this equation, and to get the final more simpler value of the k instead of this complex equation. So rest I am going to do the with the further with the derivation. This is our last equation. So I am putting some of these suggestion over here. So this we have discussed before. What what was the discussion? It is the this is the length of the box in the x direction, starting with the zero with the total length. Let's suppose this is L. So length of the box starting from 0 to L. So what would be the wave function? Wave function is starting over here. So the wave function is 0 at this point, and when it is going to end, and this will be 0 at the point L at the both side of the box. So this is written over here, x will be equal to 0 when, that means when this is the x direction, when the value this x is 0, then psi will also be equal to 0, and then this x will be L, then the psi will also be 0. So main important is the wave function will be 0 at the both end of the box. So because this is the particle in one dimensional box. So when the second condition is applied, you can apply also this condition. So actually this is the when the particle over here, there is actually the particle is not moving. So this is insignificant to consider this point. Actually, when the particle is going to start, and let's suppose it is here or here or here, whatever the distance it has traveled, this is important. But when it is at the start, that means this is the insignificant to consider the or to calculate the movement of the molecule in one dimension box, the part, because the particle has not moved right at the starting point. Even you can verify by applying this equation. So when actually I'm putting the values of let's suppose condition 1 over here, x psi will be 0 and x will also be 0. So this whole factor becomes 0. So that's why I have said there is no significance over here to consider the particle at point 0, because the particle has not moved right now. So when you apply the second condition, so that means when x will be equal to L, that's the particle, the total length it has traveled. Maybe it depends on the less than L value, but I am going to consider the total length of the box that will be equal to L. So when x will be equal to L, the psi will also be 0, as we have discussed before. So I am going to apply this condition to this equation again. Again, psi will be equal to 0 when x will be equal to L. So psi will be 0 and x will be equal to L. So I'm just replacing the value of the x and the psi by considering the second equation. So this equation is this, and then if a is neglected, because I want to because there are the both unknown factor a and k. Actually, now I am going to just to neglect the value of the k, and we will find out actually what is the value of the k later on. To make more simpler this equation, so this equation will become like this. I am just skipping the value of a over here. Let's suppose this is the neglected value, so this equation will become like this without a. And then no, this is the mathematics formula. So very simple formula. I'm just going to get the output of this formula, and this is this when sine pi equal to sine 2 pi equal to sine 3 pi equal to so on 4 pi, 5 pi, and 6 pi, and that the value will be equal to 0. This is the mathematical notation. We are not going to discuss this formula here, but we are going to apply this formula to get our the value of the k from this equation. So if this is equal to 0, that means sine n pi will be equal to 0. So n is the 1, 2, 3, 4, 5, 6, and so on. And this is the same equation. Just I am getting this equation into more simpler form. So sine n pi will be equal to 0. And now we can compare the both equation. Here sine will be equal to 0, and this is the because here all these are the constant 8 pi square m e h square, these are the constant. That means it may be equal to the theta, and this may be the sine theta, and here the theta is the n pi, as we discuss in the Schrodinger wave equation. So sine n pi will be equal to 0, and sine this will be equal to 0. That means again this equation will be equal to this. So I am going to compare this equation. This will be equal to this, and now what is happening? You can cancel out this sine psi over here. This is the cancellation. This equation becomes like this, and then after taking the square root of this equation, this will become n square h square equal to 8 pi square m h square l square. This square under root is cancelled out, and l square will be here. So this is the just the by taking the square. Now moving to the final version of this equation, you can cancel out the psi pi square. That's why we have taken this square. Otherwise, there is no need to take this square, because here we want to get more simpler form. So there is a pi square. We have cancelled out the pi square, and this equation will become like this. And then if you want to get the value of the E from here, so E, this is going to multiply, and these 8 pi L square is going to divide, and you can get the value of E from here. And this is very important equation, and this is going to give you the energy of the nth level, any of the level where the transition of the electron will be happened from, let's suppose, energy level 1 to energy level 2. By using this, you can calculate the energy of any level where is the electron there, and the difference in energy between the two levels. So later on we will actually we will calculate the energy of each of the level and the energy difference between the two level over here. So by with the energy, this solution of the Schrodinger equation demonstrates that energy of a particle in a box is quantized. And you know, in a separate lecture, we have already derived this equation before, where we discussed the quantization of the kinetic energy, and this is the same equation. So this is derived from the particle in one-dimensional box, and there we apply some other conditions. And with this equation, now with the Planck's equation, we have already discussed. This is the energy will be equal to h mu. E is equal to h mu, or delta E will be equal to h mu. This is the quanta of light. And this is the more important equation to get the value of the h mu. So by using the energy difference between the two levels. So this is an equation, that's a simple equation, and this is more advanced equation to get the exact value of the uh, uh, any of the quanta of light, because here the length of the box is there and the mass of the electron is there, and this is the energy of the any level, if it is 1, 2, 3, or the fourth level. Sorry. So here this is the application of this equation, and we will calculate later on the transitions. And this transition, let's suppose there are the particle in one dimensional box. This is the translation motion, and this is the application of the particle in one dimensional box. Actually, we will use this equation to calculate the energy difference between these different levels. Let's suppose if the electron is moving from the bonding sigma orbital to anti-bonding sigma orbital, so this is the transition. So we will apply this equation to calculate the energy difference between these two. And it may be the from the bonding pi orbital to the anti-bonding pi orbital, and maybe it is the non-bonding to the anti-bonding sigma orbital and non-bonding to the anti-bonding pi orbital. So, or simply you can n to pi star or n to sigma star. So these are very important transition which are only happened in UV and visible region. And this is the equation to apply over here to get the value of the energy difference between these different transitions. So moving to the further version, this was our the last derived equation, and here we arrived up to a sine. This is the whole factor. This actually was equal to k, and that's why I explained earlier. We want to make it more simpler because here the energy is required, and m is the mass of the electron. Again, pi is a constant, h blank is a constant, but there is no the length of the box is not given. So that's why we want to further modify this k value to get it more simpler form, and this is the way to get the more simpler form. And here I am just putting the value of E over here, and E will be equal to n square h square over 8 ml square, and L is coming out from the this energy. So I am just putting the value over here, and let's see, when you put the value of E over here, then everything is cancelled out, and what is left, this is n pi over L is left, and x is coming from the equation, and this is the actually is the k, and n pi over L, that is the k, and we have calculated the the value of the k in a more simpler form. If the particle is moving in one dimensional box, this was the constant, and that constant is n pi over L. Again, pi is the constant, and these two are important, and this was our target, and these are required for the particle in one dimensional box, because the length of the box is very important, or you can say how much distance it has traveled from 0 to here. So maybe it is L by 2, half of the length. So we will put the value of over here. Maybe it is 3L by 2. It's depend what type of the transitions are happening and what is the energy level. So when we actually finish the derivation, then we will talk about more about the what would be the wave function in energy level 1, energy level 2, 3, and the so on. So here I am going to conclude this one. So with this, we have rightly achieved the value of the k, which is equal to this, and why we have moved this complex to more simpler form, because here we need the what is the distance of the particle or the electron it has traveled within the box, or within the box mean in one dimensional box, and one dimensional box mean that is the translation motion, because if it is only the moving to the one direction, it should be a translation motion, and all these transition are considered as the translation motion of the particle. So I'm going to end the lecture over here. So we have arrived over here. Now in the next lecture, we will calculate the value of A, what is now the constant A, and then you will know exact the value of the wave function. When you put the value of the all of the parameter here, you will calculate the wave function, And another important parameter is the what would be the probability of finding the electron. And this is again very interesting and encouraging. You must know what would be the possibility of the electron. Where is the electron right now here? And these are the minor things. But after completing this course, you would be efficient to find out everything about the particle or the electron moving in any of the direction, what will be its density at any point, and what would be the value of the wave function over here. So let's see, we will do in the some of the lectures over there.